I am Aspen Albert, and here is my Lab 2 Projectile Motions lab. The introduction to this lab consists of the comparison of position of a projectile affected by gravity as well as drag. Gravity is the gravitational, the force that is here on Earth that makes an object come or pulls it towards the ground, versus drag, which is a force of aerospace, which opposes the actual direction that a system is going through within the environment. The object that we used was a paper ball with a mass of 13 grams. And we did this using the Tracker app for experimental model and GlowScript for the computational model. Notable formulas used throughout this experiment consisted of the position update formula, which tells the change in position from our final versus our initial, the force of gravity, which in this case we use negative mg due to us being on Earth, velocity update formula, which tells the change of speed within an object, and drag force, which was mentioned previously. During the experiment, we made sure to get a paper ball and we threw it into the trash can, making sure to calculate where the ball began versus where the ball ended when it first hit the rim of the trash can, and nothing more. In my graph here, the computations are kind of wonky due to the fact that I didn't properly center the mass points as I should have, but as we make our way over to the actual um, computations made using GlowScript, it's more clear. For GlowScript, the ball's mass was 13 and the ball's position was 0, 0, 0. But the ball velocity was vector 1.4725 and 1.637 since we started at a raised place. T is 0, delta T is 0.33. Gravity is 9.8 as it usually is since we are on the Earth, and this is with the drag being 0. So when you run this program, you can see that the position of X in time is going at a constant rate with no changes. You can see that in these two graphs, and the position of Y is not really going in a constant. As we go back to here, okay, now we're going to talk about drag. Now, if my drag was adjusted to 0.0545, the drag slightly, it lessens the steep of it. So instead of being a very steep parabola, it starts to kind of round out a little bit. And if the drag went up rather than down, say it was 5, the the drag would be far more steep, or the graph would be far more steep when it comes to the parabola. The deviation causes. Causes of deviation were due to user error while tracker. Again, regarding to the lack of centering in the position or the system that was actually moving throughout the surroundings, which is the paper ball. Errors with decimal surrounding, as well as the outside forces, like the drag forces that could have been stopping the object once the air was going against the force or going against the opposite of the direction that the ball was going in. Terminal velocity and what it means. Now, in the constant position X graph, we can see that there is a terminal velocity due to there being a constant velocity. Now, in our Y position, there is not a constant due to the fact that there's not a terminal velocity due to the fact that there is no constant force. The force differs, so that it will not end. Now, what if? What if the ball was thrown up at the same speed? If it did, it would be coming down at a shorter time and hitting the ground rather than the way that it kind of took some time during the trajectory equation. And this is due to the equation T projected equals 2v initial sine theta divided by grams, and T up, which will be the ball being thrown straight up, equaling 2v0 divided by grams. That's all. Thank you for watching.